All right.
So welcome everyone to today's database internals meetup. My name is Verti Chu, and today we are going to look into chapter 2 of the database internals book by Alex Petrov. And in this chapter, we're going to look more about B trees as we've already did in the previous 5 chapters. And in this chapter, we will look into a series of different B trees. Can we go to the next slide? So, as we've been looking into different, for example, we've been looking into quite some knowledge into B trees so far, and we can see like although B trees might have multiple different variants, there are a lot of things in common as well. So, for different kind of B trees, what they are in common with are the tree structures, the way they balance, which means like split and merge, and also the lookup and deletion algorithms. However, different B trees also different depends on their different ways of how they deal with concurrency, and also how do they deal with on-disk page representations, and also do they have sibling node links? Maybe some do and some doesn't. And there's also the maintenance process difference. Next slide, please. So in this chapter 6, what we will cover about is 5 different type of B-tree variants, namely copy and write B-trees, lazy B-trees, FD trees, BW trees, and cache oblivious B-trees. Next page. And for today, what we will be working on are 2 to 3 types of B trees depend on our time. So the first one we'll be covering is the copy and write B trees and lazy B trees, and then FD trees. Next slide, please. So let's look into copy and write B tree. So when we are having concurrent operations, what we really care about is in these concurrent operations, we want to guarantee data integrity. And if you still recall from our previous meetups, we've been discussing different latching algorithms, right? We've looked into complex latch, like how do we do with it, in our previous meetup, like when we were going through chapter 5. And do we really need to do complex latch all the time? There is actually one way to bypass that, which is use copy and write. Next slide. So when there is concurrent operations, imagine a situation whenever the page is about to be modified. Copy and write B tree follows the 3 steps that's been listed here. The first thing is it will first try to copy its content, and the second step is modify the copied page rather than the original page, and the third step is a parallel tree hierarchy will be created, and then the tree will switch from the previous one to the new one. Next slide. So in this, following these 3 steps, what we will be able to get is the readers and writers will have the following characteristics. So for readers, it can access the old tree versions concurrently because the old tree versions is always still there while the writers are trying to write on the modified pages, right? So writers access modified pages have to wait until preceding write operations are complete. So there is readers that are freely able to read the old tree version, and then there's writers modifying the copied page and then waiting for the previous writes. Next page. And what this gave us is after the new page hierarchy is created, the pointers to the topmost page is automatically updated. This might so far sounds a little bit abstract. So now next page, we will look into one example here. In this page, you can see this graph actually demonstrate about how we interpret like after the new page hierarchy is created. From the right hand side, as you can see, there is the new tree node, And then from the left-hand side, you can see in the light gray ones are the current B tree, right? And then while there is new writes happening, there will be like new writes happen to the bolded black side of this graph. And then once that one is complete, which represents new page hierarchy is ready, the old tree root will actually get switched into the new tree root. And you can see from this graph, new pages are being linked into this new tree, and there are also certain areas in the previous old tree that did not get modified, which is, for example, the left corner area of the current graph. Those ones are not really being modified, so the new tree can just still reuse the unmodified previous pages. Next slide.
May I have a question here?
Yep.
Yeah, so actually, I have some question regarding the simultaneity write, right? It's for example, I have a 100 TPS of write. Can I understand that in this moment we will have 100 new tree will be created?
No. So, from my so I understand, from the book, like it's saying like whenever there is multiple writes, all these writes actually need to wait the preceding writes to complete. However, it's allowing concurrent read operations because read will not really be impacted, right? So, for example, if you have like 1,000 read going on there, like previously, in the previous chapters or whenever you look into a B tree, what we really worry about, for example, using different latching algorithms to guarantee is that whenever you have a read, it wouldn't really have any conflicts, while some other operations is trying to write into the tree. Because whenever you write into a new node, there will be like whenever you write into a leaf node, say, there will be operations propagated from the leaf node upwards. For example, different merge and split operations. And copy and write, actually, what it guaranteed is the read operations before the new tree is constructed will not be impacted. So, like until all the way that the right part of this graph, which is a new tree, is being constructed and linked into the current old trees and modified part, the old tree will still be used for all the read operations. And
I have a
as your
question
question
here.
asked, multiple writes will happen like with the on the new tree side. Yeah,
I
please.
have a question here. So you said there is at most one write, but you can have multiple concurrent read operations. Is that right?
Yes, that's my understanding. Yeah.
So if you have a write and then the write is doing the thing, and then you have later you have a read, but the read is going to return the old result if both of them are trying to modify and read the same key.
So this is a good question, and I think like we will resolve your question like in just next 2 slides, because what you're asking, yeah. So what you're asking here is what if like the read is trying to read something that the write is literally about to write, like with a new value, right? And this in this situation, like the read will read the old style data. However, once the write is committed and once the write, once the new tree is being constructed, like further read will read the new write result. So there is this timing thing. Yeah. Next slide, please.
Okay. So what you said here is, can I understand that write is only one? Is that the same concept of linearity?
I think so.
Okay, then meaning that if the database using P3 here you presenting, they will supposed to be supporting linearity all the time, right? My impression is I think the Masaka PVT he have a kind of presentation PVT another lecture, not sure I understand correctly, not all the database support linearity, but they are using B-tree.
Are you talking about the replication linearizability?
Uh, I think in
Because that's
database
a
also
different
have,
thing.
okay, maybe I mix up.
Yeah, linearizability is a concept in when you have multiple replications of the same data. But here we are discussing the indexing structure inside of a database. I don't know if I have answered your question. So it's a totally different concept here.
All right. Okay. Maybe I could check it later. But I mean, that will be have to do it readability one by one, right? Even though we have like hundreds of the TPS, right? They have to be one by one in these cases, right?
Yeah, I think from I might be wrong, correct me if I'm wrong, but by reading the book, I think it says a write needs to wait for preceding writes to finish.
Yeah, but this case could be a single node, right? There is no distributed system involved. It's a single node database and has multiple processes that try to write or modify the same thing.
And for this, I would say it's a serializable. It's a serializable write. So in the database, I think the concept will be serialization. This
No,
is
that's for transactions.
Yeah, transaction
There is
only.
no transaction
Right.
involved here.
Well, yeah, Masaka, I agree with you that if we have single node, this single node have to be linearity, right? In these cases, and then still
Yeah,
the same
single node
question
is
remain.
always linear, if I'm right.
Yeah.
It's always linear.
Yeah, I mean that's my question, though, because what we test here, I did several kind of the performance tests. The single node is more, it's in Cassandra database. It's reaching out to thousands of TPS though, even single write for writes. So I mean, how it able to supporting such a high TPS write if we using linearity? I'm not sure that it's a valid question, but I have a doubt there actually.
For that, I'm not sure. Is Cassandra using LSM tree for indexing or B tree?
My understanding should be peachy. I don't know anyone have different view. Yeah, we could put it later. Sorry, I
I'm
don't
not
But
want to
is
sure.
it
like.
for copy and
Use
write feature? I'm not sure about Cassandra like internal implementation either. We can definitely look it up like later and discuss it offline. But anyways, yeah, someone comment say Cassandra uses LSM tree, then that will be covered in our next chapter. Okay, thank you. Let's continue. So with regards to copy and write B tree, as we can see in the previous slide, that this is how it looks like and 3 different steps of how the algorithm works. So it actually gave us 2 major downsides. The first one is it requires more space. Although we wouldn't really keep the old page for a long time. It's actually a fairly short time because once we have the new page ready, we can just switch to the new page and then reclaim the resources used by the old page is fast. However, it still means we have to retain the old page before we get the new page ready. So this requires extra space. And then the other downside is processor time, because when we try to write on the new pages, we need to copy the entire old page content first before we perform any write operations. Next slide. However, the thing is, since B tree are generally shallow, if you recall, like from our first time talking about B tree, we actually emphasized that the B tree, like although in our demonstration, like all these B trees node is like, like 0 of 5 different slots for you to put your values in. The real B tree being used are generally quite shallow with a pretty fat node. So this means because the nature that the B tree being used are normally shallow, is the copy on write B trees simplicity and advantages still outweigh.
大家可以先填
Next.
一下，然后我们再来一起看答案。
Can we mute everyone?
Yeah.
Okay. Next slide, please. Thanks. So after talking about the downsides, let's look into the advantages of copy and write B tree. So let's look at in the readers and writers. For readers, it requires no synchronization because written pages are immutable and can be accessed without additional latching. This is what we just explained and demonstrated. And then the second part, and then from the writer's side, it actually is able to perform against on the copy pages, which means readers will not block writers. Next page. And from that, we will be able to see this leads to two advantages. The first one is no operation can observe a page in an incomplete state, because I think this comes back to the question Masaka was asking earlier, which is like, oh, like if there is another read also happening and then there's another write happening, what will this read operation get, right? So no operation can observe a page in an incomplete state. And then the second thing is system crash cannot leave pages in a corrupted state, because the tree will only be modified once the new tree is being constructed. Yeah, next.
Oh, I have a question here. So when you say there is no incomplete state, it means that if one write copies, say 4 pages from top to down, do you mean they have to be automatically replaced to the original tree so that there is no partial result?
Yeah, so I think like it so copy and write is emphasizing on once you do so there are 3 steps, right? Once you decide, oh, you want to write this way, you have to copy it and then provide your updates to all these new write nodes. And then once these write nodes are all complete and they are all able to link to the previous tree, because there are also many trees in the previous original tree that are not being touched, right? So those ones are intact, and then you link back to those ones, and then at this stage you form a new tree, and then only when you form this new tree, this operation is considered as complete.
But you have to do for every page that has been modified at once. How do you do that? If you are not using a lock, how can we achieve that?
You can find more about this in the future slides.
Okay.
Okay, let's come to the next one. So let's see one implementation of the copy and write algorithm, which is LMDB. So LMDB stands for Lightning Memory Mapped Database, and you can see it is is actually used by the OpenLDAP project. It's a key value store, and here's also the link to its GitHub page if you're interested. Next. So what LMDB does is it implements the database as a single level data store, and its read and write operations are satisfied directly through the memory map, which is why this is a single level data store. And this also means it does not need additional application level caching in between, and its pages require no additional materialization as well, and also its reads can be served directly from the memory map. Next. So whenever there is an update, every branch node on the path from the root to the target leaf is copied, and this leaf and all these nodes and leaf node will be potentially modified, depends on if there is any split and merge operations, and the rest of the node remains intact, which is corresponding to the left part of the demonstration graph we just saw. Next. So let's look into the the root node and then the other nodes. So the first one is the root node. In LMDB, root node only have 2 versions to keep. So it doesn't really need more versions, it only needs 2. The first one is the latest version, which is the one that readers all access and will be able to retain all these like current value of this root node. And then the second one is the new root that new changes will be committed later. Next. And when it comes to the sibling nodes, as we always look into, like in LMDB, because it is a append-only design, so it does not use sibling pointers, and it has to ascend back to the parent node during sequential scans. So this makes it always need to jump a little bit back and then go down to its actual siblings. Next. So what this gives us is it's by nature have its multi-version characteristics, which means it's able to support MVCC. And then the other thing is readers can run without any locks, because like as we've mentioned before, like readers will not really block writers, and readers will always be reading the first version of the root node, right? Only the second version of the root node are the new values that will be committed. Next. So after we've talked about copy and write B trees, let's move to another type of B tree variant, which is lazy B trees. So for lazy B trees, what it does is it's trying to reduce the cost of updating B tree, use some more lightweighted concurrency and update-friendly in-memory structure to buffer updates, and then also to propagate them with a delay. And here you can see a sloth here, right? So the reason why I put a sloth emoji here is like sloth wouldn't really react until it realized it has to. So that's why we have a sloth representing lazy B trees. And next page. And for lazy B trees implementation, there is one example provided by the database internal books, which is Wired Tiger by MongoDB. So what it does, as you can see, its logo is quite interesting, also a different type of animal. And so what it does is its row stores B tree implementation uses different formats for in-memory and on-disk pages. So so before these in-memory pages are being persisted into on disk, right, they have to go through something called reconciliation process. And I think this reconciliation process is what makes white tiger or say lazy B trees being special. And you can visit their GitHub page as well. It's an open source project. Next page. So when we come to lazy B trees, there are 2 concepts to know in mind before we look into it in more details. The first one is a clean page, and the second one is update buffer. So what is a clean page? So the clean page consists of just an index and is what is initially there, and an update buffer, as its name indicates, is a buffer to save all the updates, right? So whenever you have an update, before it actually make any changes and have an impact, it's actually been first saved into this buffer. Next page. And here is a graph to demonstrate. As you can see, like the major trunk of this tree are the clean page, and you can see there are several gray boxes, and these ones are the update buffers. So whenever there's changes to come, it wouldn't really change the clean page directly. It will save all these updates into the update buffer for later use. Next page. So how exactly does it do it? The first thing is when it tries to access during reads, when you have updates, right? Like updates being saved into this update buffer, and then when you're trying to do a read, are you going to read the clean pages only and ignoring all the existing current updates that's already been there? No. So what it does is when reads happen, the contents are being merged in between the clean page and the update buffers content, so that like by merging these two, it will be able to return you back with the most recent data. Next page. And when a page needs to be flushed, the update buffer contents are being reconciled with the page contents and persisted on disk. So basically it means like when you're about to flush a page, overwriting will happen to the original page, and the combined result will be the one that's been persisted on disk. Next page. And how exactly are update buffers being implemented? According to the book, it's been implemented using skip list. And if you still recall our previous meetup, I think in last week, Masaka, like in the session that he hosted, he actually showed us what skip list is. And the reason why skip list is being used here is it provides a better concurrency to the profile. Next page. Yeah. So both the clean page and the dirty page in White Tiger have in-memory versions, and they all reference to a base image on disk. So as you can see, they have this in this graph. There is in-memory versions for both, and then in dirty pages, besides the index, it also have like those update buffers, and then they also have their base image on disk. Next page. And the advantage of this way, of doing it this way is, first, the page updates and structure modifications are performed by the background thread, which means like it doesn't really interfere with the current thread, because all your changes are first being buffered right into those update buffers. And then the second advantage is for read-write operations, it will not have to wait for them to complete. Next page. So after seeing the previous example on the lazy B tree, you can see like what we do is we have this, like, each node have like a clean page and also dirty page, and dirty page have their buffers. And then whenever you have writes, you write into those buffers for each node. So here comes a inspiration light bubble, which is, why not group nodes into subtrees and attack an update buffer for batching operations to each subtree instead of individual nodes? Would that be more efficient? So here comes our our next B tree variant, which is called lazy adaptive tree, also in short LA trees. Next page. As you can see in this page, is like in this page, like we have a graph here to demonstrate. So in LA trees, there are buffers, but these update buffers, rather than for each single node, it tracks all operations performed against the subtree top node and its dissidents. So you can see here are, in this graph, there are three buffers. One is a root buffer for the root subtree, and then there are also two child subtrees, right? And then for each of these child subtrees, it has their corresponding subtree buffer. So it means like our buffering is no longer just on individual node and have to keep them respectively. We are trying to do this kind of like batch of updates. And whenever there is an update happening, it will be done in a recursive and cascading manner. So in this graph, when you can see in the gray box, right? So when a update comes first, it will be first saved into the root buffer, and then because these updates, like on a normal B tree, it will actually impact the subtrees, right? So as you can see in LA tree, these impacts that will happen from top to down is actually not going to immediately impact the corresponding subtrees or the subtree nodes. They're actually being collected in these subtree buffers. And then once these subtree buffers save them, that will be marked as one operation's been completed. And when it comes to read, it will be similar to how White Tiger does its read, which is also like when a read is happening, it actually try to do a merge and then gave you the most up-to-date result. And then whenever you try to flush into disk, these buffers for different subtrees will actually be combined and then being flushed into disk. So that's all we have for today's discussion. Like we looked into several different B tree variants and then also have looked into like how their implementations and also what their advantages and downsides. In next meetup, we will look into more about FD trees and the other two types of B tree variant in chapter 6. So we also encourage you to read more about FD trees in advance because it's a fairly abstract data structure. And we will also post the recommended reading materials of a paper in our Slack channel as well. So any questions about all the things we've come through today?
Yeah, I do have a couple of questions actually. The first
Yes.
one, the subtree buffer, I didn't really get what you mentioned, BUD. So how the subtree buffer is refracting to the chain inside of the left side of the page over there? Is that a pointer, or how it's able to capture subset of the change in the block here?
So these buffers are just like so how to say it? So when there are updates that's for example like batch inserts updates or delete, um so all the tree all these buffers in these trees will be um applied in one go. So do you mean like how will they will be applied to this tree, or do you mean how this
Yeah,
buffer will
actually, for
be?
example, we give they one example, right? I wanted to update a rec a row of the table. This row I changed the last name, right? Only. So the left side you see here is still the old value, right? And the buffer subtree buffer I get that will be represent a new value,
Yes.
correct? And
Yep.
and then my question here is how this new value is refracting back to the old value. If they are using a link or Hashimate or kind of pointer. Do you have any idea?
I
Because I read the book, I don't see detail about this actually.
Yes, I didn't mention it. I think the book here is trying to introduce like the LA tree algorithm thought rather than the actual implementation details. Um, and I think your question about how exactly is this subtree buffer is been for example, how would you define how big your subtree is? How would you group them together and give them a buffer? I think these are the actual quite detailed bit of how it's been how it's been implemented.
Oh, okay.
So with regards to the scenario that you are describing, um, so it is about like when you try to insert a data record, in that situation, like a new record will be added to the root node, right? Sorry, will be added to the root node buffer. So in this graph is the in the first root node buffer gray box, and then it will also be like cascading like all the required changes to the lower level tree buffers, and then that is how it's finally reached to the leaf node. So yeah, so the book doesn't really say like for example exact like detail about how root buffer like how different subtree buffer is linked to the subtree. Yeah.
Okay. Okay. So you mean the root buffer it actually indicate which page will be modified, right? And then the subtree buffer down there will indicate what is the value will be changed. So from top to the bottom.
So root buffer and subtree buffer are all just buffers saving changes. So they are saving all the updates that will happen to to the subtree.
So
Okay.
the root buffer or any buffers for the subtree should have something to tell you that this record's being added to which page in the subtree. Otherwise, there is no way that when you flush the root buffer, you will find the corresponding pages. So I assume it has some page ID associated with the key values in the root buffer.
Yes. Yes, so apparently root buffer will be saving about, for example, how you want to modify this subtree.
Yeah.
Like if it's just say, oh, insert a value, then you don't, right? Because this root buffer is just something to to record like changes happening to this subtree. And the reason, or say the advantage or the initiative why LA tree is doing it this way is just because it thinks is too is it wants to provide like a larger granularity of recording these changes.
Okay. So I just would like to compare with the previous one, right? We have a version. So here we use actually a kind of buffer, so that we don't really need to copy another full set of the data, right? That I think it is the
Yes.
first beneficial of doing that. And then the second thing I'm thinking, or my understanding is, whenever the pivot one or this one, before you flood into the disk, you have to merge it into the page anyway, right?
Yeah, so that's called reconciliation. So
Yeah.
both LA tree and the previous weird tiger example, they are both lazy B tree. So imagine the sloth, right? Like it doesn't really copy things in advance. It doesn't really do anything until finally it has to.
Right. Right.
Does it care about durability? Because anything in the buffer will be lost if the power is off.
That's a good question. I don't think the book has mentioned it, but I think maybe there will be some way for them to emphasize on that, because apparently when the book is talking about lazy bee trees, it only says it doesn't really like it only says it doesn't really do it like in how to say it only says it's trying to reduce the updates
Memory. Yeah.
updates cost. Yeah. And it actually says is friendly is trying to do an update friendly in memory structure. So all these are actually
So I
in
guess
memory.
it's not important. Things lost is lost because it's a index, right? It's not the actual data pages. It's just the index.
But it still wants the updates to
Yeah.
be recorded. Maybe they have some different ways to make sure that all these these buffer contents are also being recorded. Like I was thinking about this actually as well. And I thought maybe they have like some write ahead log happening before they do all these like tree operations. So I mean, in parallel, I think if I recall correctly, in DDI it also mentioned that for this B tree, like just B tree implementation as a whole, rather than different B tree variants and details, it says like all these B tree implementation in databases actually also maintain a write ahead log, so that all these changes will be put into write ahead log before there's new changes actually made on this B tree, which solve the question that where if that is the case, for example, for these actually implementations, either for Wild Tiger or for this lazy adaptive tree, then it will be able to solve our questions for what if there is like, what if the database crash and the buffer in memory got lost.
Yeah, my understanding the same. So they should have a checkpoint, right? If you apply into the flood to the disk, users
Yeah.
point to that places. Uh, okay, that makes sense. I mean, I'm not sure the book it doesn't mention that, but that's my understanding also. Yeah, I have one more question. Could you go back to another couple of slide? There's one page talking about the application catch something. This one I don't
Let me know which one you want me to stop.
back. I-
Is that what application?
Yeah, there's one application without application catching something.
Do
Back.
you mean?
Which tree are you talking about?
Oh, I cannot remember.
There are so many different variants.
Yeah, can you set the application? I think this slide only have one application though.
Let me
Search
try to.
Because that one
Gosh.
point you're saying that without application catching, but that point I don't really get. Oh, I have to book my end also.
Oh, I think you're talking about LMDB, right? I think that's in
Mm,
LMDB.
Okay, so that's here.
Copy. Yeah.
Yeah,
I think maybe next slide.
Yeah, this one.
Here,
Yeah,
here.
Okay.
Read and
right,
write.
right. Yeah, so how, I mean, read and write operation are satisfied directly without additional application level catching in between. So can we, I don't know, do we have any other database using application catching in between? This one I
So,
don't. Mhm.
I actually didn't really compare with other databases, but I think the reason why it says it does not need additional application level caching is because LMDB is a single level data store.
Yeah, it really does matter because, for example, for the other database, right? No matter you are Oracle, MySQL, we in application layer we finish the logic and then we just use the JDBC or something connect to the database and then we submit the request SQL, right?
Yeah.
So I don't know where the catching in the application layer.
So
don't
so
really
I
get.
think it's because LMDB is single level, so it's able to just get it directly. Like if it's not a single level data store, it might as well need to get like caching like before it reach the final level that it's
Oh,
looking into.
okay. You mean the cache in the database is cell, but that is database layer of caching though.
Um,
Because whenever we talk the database engine, right, we have the different component like store
I
engine.
think
We have
this question can be which means read and write operations are satisfied directly through the memory map. Yeah, because you have this memory map, so you'll be able to just get it directly. So you don't need to cache anything. But your like I think your question will be it will be good to answer your question if we are able to find some other databases that requires application level caching, and we
yeah,
can
that could
see
be
in
because
like in comparing.
like my SQL, I mean, we all putting the page and the link and so on in the cache, right? So that's why I kind of not sure why I mean, indicate this sentence here. You just in case you guys know, but that I bring my questions over when I read it anyway.
Trying to look up.
What does the read and write operation are satisfied directly through the memory map? I don't understand what this means.
I found an answer that might be able to help you on Stack Overflow. So one second, if you click open that.
Sorry, I have too much things going here. Let me open this. Is this one you are looking for?
Oh, we couldn't see your slide, your web page.
Oh, it's because
Yeah, maybe another screen. Yeah.
Yeah, I'm sorry about that. Give me a sec. Are you able to see this now?
Yeah. So
Oh,
I
you are
think the
talking the
top
OR
answer.
mapping.
Yeah. So
That is
this
another
answer
framework,
is
though. Yeah, I
yeah,
know.
but
Oh, Hibernate is OR mapping. That is the, I mean, middle layer of the database framework to do the mapping. Yes, for sure. That is the mapping in the
so this one
application
is
layer.
about application level cache. The reason why we use application level cache, right? And I think apparently in the LMDB example, because we don't really need to fit this need because everything will be able to fetch directly from the memory map.
Yeah, I think it provides a handle to the memory so that the programming language can directly access the memory. So there is no need to do another level of
Right.
translation.
My understanding is the, I mean, so rational database, they have kind of complicated join, a kind of foreign key and so on. So that's why they use the OR mapping or hibernating to do the kind of actual logic and the catching over there. But I'm not sure hibernate supporting non-SQL as well. Because what we're talking here is the memory database, right? Like level DB and so on. Normally their storage is key value only. We don't really need this kind of application layer of the cache. So why
Yeah.
he only mentioning this database? That's why I kind of
Yeah, that's a good
LMDB.
question though, and also like according to the book, it also emphasized that LMDB doesn't require a page cache. And it doesn't require a write-ahead log either. It doesn't require checkpointing or compaction. And according to the book, that is because it's a key value store and it's a single level data store. So
May
I
I
think it will
chime
be
in a
good.
little bit? Yeah, it's not that memory cache in app level. If you go back to the slides, that memory map is like in the OS level. That if we use the memory map, which we call the M map, and it will bypass the operating system's buffer cache, and then the user space will write to the disk directly, and if there's no no disk in the in the memory, and it will trigger a page fault, and then the page fault will read the disk directly without buffering. The reason why is that because it will copy paste like the each node, and then it's hard like to align in different pages, because as you can see in the copy on write, that it just operate the whole tree that will create a new root and then like a subtree accordingly, and it's very hard to align each pages. So that's why it will bypass the OS buffer and then use memory map directly to visit and modify the file system. And at the beginning, that's the reason why it doesn't need the write high log and the other like recover mechanism, because the write will directly to the disk. And but I think the MongoDB, the first version of the MongoDB is using this memory map technology, but it has a lot of disadvantages. And I think in this year's CIDR, there's a paper like to modify all of the disadvantage of using memory map in database. So then in the later version of the MongoDB, it just reuse OS buffer and just skipped the memory map. So this memory map is the memory map in the OS level, not the application level.
I think the MongoDB, after they got funding or after they went IPO, the first thing they changed was get rid of the memory, using the memory map.
Right, because there's a lot of pitfalls of memory map, and it's hard to control and hard to fine tune the performance. That's the reason MongoDB just abandoned the memory map.
Yeah.
Also, David, just for my understandings, for the latest version of MongoDB, they abandoned the memory map and they come back to use the application layer of cache. Is that correct?
Not the application layer, the OS layer. What we
OS
talk
layer.
here all about the database is talking about the buffer in the
OS.
OS level. There's like
Okay.
no use of application. Yeah.
Oh, okay.
The database under the operating system and the disk. That's the all stuff we are talking about.
I see.
I think Elasticsearch is probably still using the memory map files.
Yeah, probably. Yeah, because it's very convenient that we don't need to care about like the OS buffer. We don't need to care about like the disk zip. It's very convenient. But I think eventually Elasticsearch will abandon because there are so many pitfalls. If you are interested, I can put the paper in the Slack channel. It's a very interesting like insight.
Let's do that.
Okay,
Thank
yeah,
you.
thank you.
Thank you, David.
Thanks, David.
David, I remember that last time in another discussion, we also talking about similar thing in the Kafka. Is that the same concept? Kafka write very fast or Redis write very fast. They pass through the OS, I mean, catching or swap, right? Is that the same thing?
That's another like technology in the kernel side. In Kafka, it uses the send file or file send. I forgot the name of the API. It's different from the memory map. It's the performance is better than memory map. It will reduce one context switch, but it's not the bypass kernel. It's bypass the user space. So the technology is different. And also there are other like technology like to bypass the kernel. For example, for like some new technology in terminal like IOU ring or like infinite bed, it will just bypass the kernel side and to the network card will talk to the user space directly. So there are very like many different technologies that to improve the performance, but it's not exactly same here.
Okay, yeah. I mean, just sometimes easy to make ups. Thank for the clarification.
Thank you, David. Any more questions? If no, then let's see each other next week. Thank you for attending our meetup today.
All right.
Thank you.
Thank you,
Thank you.
everyone.
Thank you.
Thank you very much.
Appreciate it.
Appreciate
everyone.
that. See you
Bye.
next time.